preheating air by geothermal water in a tube bank. So this is the question. In an industrial facility, air is to be preheated before entering a furnace by geothermal water at 120 degrees Celsius, flowing through the tubes of a tube bank located in a duct. Air enters the duct at 20 degrees Celsius and 1 atm with a mean velocity of 4.5 meter per second and flows over the tubes in normal direction. The outer diameter of the tubes is 1.5 cm and the tubes are arranged in line with longitudinal and transverse pitch of SL equal to ST equal to 5 cm. There are 6 rows in the flow direction with 10 tubes in each row. Okay, as shown in the figure, and after this I will show you a figure for this question. And the question asks us to determine the rate of heat transfer per unit length of the tubes. So this is the figure for that question. Okay. So what we want in the question mentioned that there is air flowing over the tubes with mean velocity of 4.5 meter per second and then temperature is 20 degrees Celsius. So ST and SL is the same, 5 centimeter, and we have T surface at 120 degrees Celsius and diameter for the tubes, outside diameter for the tubes is 1.5 centimeter. So here we do not have T exit. So at this point we will assume that mean temperature TE plus T1 divided by 2 is equal to 60 degrees Celsius. Why? We need to determine the properties at the mean temperature in order for us to execute and to find the Nusselt number equation, Nusselt number or rate of heat transfer for this question. Okay, so we assume the mean temperature is 60 degrees Celsius. So at your level, you might not need to assume the mean temperature because T exit will be given in your question. Okay, and all these properties will be given. Okay, the density of the air will be evaluated at T equal to 20 degrees Celsius because we want to find what is the mass flow rate of the air into the tube banks. Therefore, that's why therefore we need to evaluate density of air at inlet temperature. So here we have density air at inlet temperature is 1.204 kg per meter cubic. So as in the previous video, in my slide video, I already explained that we want to find the Reynolds number for a tube banks. We have to determine the V maximum for a flow. And to determine the V maximum, we have to determine whether that arrangement of the tubes is in inline or in staggered arrangement. And in this question, already mentioned that it is in inline arrangement. Therefore, V maximum that will be used in order to find the V maximum is V max equal to ST over ST minus D times with velocity. Then after you get the V maximum, you have to substitute into Reynolds number in order for you to know what is the value for the Reynolds number. After you find the Reynolds number, you have to check on the table 7.2. Okay, here we have arrangement, range of Reynolds number and correlation. So if you have inline, you you have your inline arrangement in the question, and then you have to compare and check your range of Reynolds number calculated from the V maximum, okay? And then after, let's say your Reynolds number is in the range of 100 to 1000, therefore you will calculate by using this equation. So you will find what is the Nusselt number. And then if this table is for Nusselt number for number of tubes in a row that greater than 16. Okay, what if you have Nusselt number below than, number of rows below than 16? You have to refer to table 7.3. But you still have to refer to table 7.2 because we want to find what is the Nusselt number. Table 7.3 is only to find what is the correction factor. This is the equation for number of rows below than 16. So you have to calculate the Nusselt number D from table 7.2 and then find the correction factor F from table 7.3, then multiply both to get what is the Nusselt number for your number of rows below than 16. So for a number of rows below than 16, you have an additional steps to follow in order to execute the Nusselt number. So let's do this question. So the first one that you need to do is Reynolds number. So you have to determine what is the Reynolds number. So Reynolds number equation is rho V maximum times with D outer divided by mu. Or you may use Reynolds number D equal to V maximum times with D outer divided by kinematic viscosity. It depends on you which of these equation that suits you well. So at this, from this equation, I will use Reynolds number rho V max D outer divided by mu because I already have all this information. Okay, information is already given in the question, therefore I will be use this equation. You may use this equation if you want to. Okay, at this example, I will use Reynolds number equation, this Reynolds number equation. Now what we want to determine is V maximum because different arrangement will have different V maximum. But now we have inline arrangement, therefore our V max equation is ST divided by ST minus D times with V. So we have to plug in all the values. So ST is 0.05 divided by 0.05 minus 0.015, and then you times with 4.5, your mean velocity of air at inlet. Okay, and you will get this velocity, maximum velocity is equal to 6.43 meter per second. Now you already calculate for Vmax. Substitute this Vmax into Reynolds number equation. So your Reynolds number equation becomes, so rho is 1.059 kilogram per meter cubic times with maximum velocity 6.43 meter per second, and you times with diameter 0.015 meter and divide by your mu is 2.008 times with 10 to the power of minus 5 kilogram per meter dot second. So from this, you will get your Reynolds number is equal to 5086. So your Reynolds number is 5086. Next, what you need to do is to find what is the Nusselt number equation that you need to select in order for you to determine the Nusselt number value. So from table 7.2, we know that this question is for inline arrangement. Therefore, we take a look at the inline arrangement. Next, you already determine the range of Reynolds number, your Reynolds number. Then your range of Reynolds number is in between 1000 to 2 times 10 to the power of 5 because your Reynolds number is 5000. Then you have to use this equation. So plug in all the values inside. So as you can see here, there is a Prandtl number S. This Prandtl number S is measured at or is evaluated at surface temperature. So as you can see here, there is a Prandtl number S, where Prandtl number S is Prandtl number at 120 degrees Celsius. So you have to refer the properties of PRS at 120 degrees Celsius. Do not refer your PRS at 60 degrees Celsius. Okay, only PRS. So now you plug in all the values inside this equation. Okay, second step, use proper equation. Okay, proper equation based on table 7.2. So your Nusselt number, when you plug in all the values and calculate, you will get your Nusselt number is equivalent to 52.1. So that is your Reynolds number. Okay, that is your Nusselt number. Next, what you need to do is, now we have to find the Nusselt number. This is Nusselt number for number of rows greater than 16. Am I right? So Nusselt number for number of rows greater than 16. But your question, the Nusselt number, the number of rows is, the number of rows, not Nusselt number, but NL. So your NL, number of row, in your question is below than 16. So you have number of row is 6. Therefore, you have to refer to table 7.3 in order to correct this value. This value is for this value is for number of rows greater than 16. But now you have number of rows is 6, then below than 16. Therefore, you have to refer to table 7.3. So let's take a look at 7.3. So if you are referring to table 7.3, you have to correct the Nusselt number that you get from table 7.2. You plug in all the equation and you get the Nusselt number. Then you have to correct the values since your number of rows is below than 16. So here you have number of rows is 6, which in between 5 and 7. So you have your value here. Inline, inline So you have 6 rows, and then in between 5 to 7. So you have in between. What you need to do is you have to interpolate in order to get the values for 6. Number of row 6. So when you interpolate, you will get that your correction factor is equal to 0.946. Okay. Then you have to multiply with 52.1 in order to get your Nusselt number. So Nusselt number for rows, your rows is 6, 0.946. So you times with 52.1, you will get your Nusselt number is equal to 49.3. This is the Nusselt number that you will use in order to calculate what is the value for the heat transfer coefficient. Remember, if your number of rows below than 16, you have to refer to table 7.3 to find what is the correction factor. And before that, you have to determine your Nusselt number from the table 7.2. Okay. After you determine Nusselt number from table 7.2 and you already calculate, you already refer to table 7.3 to find the correction factors, then you have to multiply both of these values in order to get the corrected values for Nusselt number. So from the equation, so that is number 2. So from the equation of Nusselt number, we know that Nusselt number equal to HD over K. Okay, this is Nusselt number equation. So you have to rearrange this equation. H equal to Nusselt number times with K divided by D out. Okay, your Nusselt number is 49.3 times with K is 0.02808 watt per meter dot Kelvin divided by diameter of your tubes or cylinder or pipe is 0.015 meter. So you will get your H value is equivalent to 92.2 watt per meter square dot Kelvin. That is your value for H. Okay. So now we want to find what is the rate of heat transfer. So rate, number 4, rate of heat transfer. So from the equation of rate of heat transfer, we know that Q dot for tube banks equal to HAS times with delta T log mean. So the equation of delta T log mean is Ts minus Te, okay, minus Ts minus Ti divided by ln Ts minus Te divided by Ts minus Ti. Okay, you have to substitute the values of Ts and Te and Ti in your equation to determine and to calculate what is delta T log mean. But we do not have the value of Te. And previously, we already assumed the arithmetic mean of your flow. But it doesn't mean that we have to substitute the assumed value into this equation. Since we want to find either we are assuming the correct exit temperature, therefore we have to find what is the T exit of your flow. So from here, we can calculate the T exit by using the equation of Ts minus Ts minus Ti, okay, exponential minus As times with H over m dot Cp. Okay, from this equation, rate of heat transfer, we already determined the value for heat transfer coefficient. As, we will determine the value or the equation for As after this. And now we know that we need to determine and calculate what is the value for delta log mean, delta T log mean. So from delta T log mean, T surface already been given in the question. T exit is remain unknown. Ts, Ti, yes, inlet temperature 20 degrees Celsius. So we have here one unknown. So to determine what is the value for the T exit, therefore we have to use the equations of T exit equal to Ts minus Ti exponential negative As H over m dot Cp. So here As we can find, H, yes, we can find, Cp is already in the properties, and Ti already been given, Ts also given in the question. Here we have m dot. We need to calculate m dot and As. So now we focus to As and m dot. Okay, to find As, we have to use one tube. Okay, one tube. Surface area will be pi dl. So if we have n number of tubes, okay, n number of tubes, therefore we have to multiply this area with n number of tubes, n pi dl. So here, how many tubes that we have? So we have 6 times with 10. So pi dl. Pi d is diameter, outer diameter. So 0.015. Okay, times with L. Since L is not been given, we have two different methods, whether you want to assume the values of L or you want to remain it as L, because in the question we need to find what is the rate of heat transfer per unit L. So it's up to you whether you want to assume value for L or you want to remain it as L. So for me, I will remain it as L. So my As will be equal to 2.827 L. So that is my surface area equation. Then we have to find what is the mass flow rate. So mass flow rate is equal to rho 1 V number of times with ST times with L. NT is number of column. It is not rows but column. So at this point, your number of column is 10. Rows is 6, column is 10. Or more so how many cubes in each row? Or I always says that this is column, like what I said in my previous video. So here we have our row 1. Row 1 is the properties, the density of air at inlet, which is at 20 degrees Celsius. So this is 1.02 and 1.204 kilogram per meter cubic. So we times with V. V is velocity, inlet velocity. So 4.5 meter per second. So do not substitute your V maximum, because V maximum is for your flows of air in over the tubes. But now we want to find what is the mass flow rate of air into the tube banks. So therefore you have to use velocity of air at inlet. Okay. Now you have NT, number of column. So your number of columns is T, or in other words, number of tubes in each rows. So times with your ST is 0.05 meter. Times with L, length. Length is not been given, therefore it will remain unknown. Like I said before, if you want to assume 1 meter, then it's up to you. So your mass flow rate equation becomes 2.709 L. Okay, that is your mass flow rate. So now we have to substitute into T exit equation in order for you to determine what is the value of T exit. Now your T exit is TS. TS is 120 minus 120 minus 20. So exponential minus, so 2 point, so we have AS. Before this, our AS is 2.827 L. So times with your H value, so 92.2 watt per meter square dot Kelvin, and then divided by your mass flow rate equation, 2.709 L, times with your specific heat capacity, 1007 joule per kg dot K. So here we have L and L, so we can cancel out this L. So you calculate, and then you will get your exit temperature is equivalent to 29.11 degree Celsius. So after you get this value, you have to substitute into delta log mean. Okay, substitute your value into delta log mean from here. So we have this equation for delta log mean. So you will get your delta log mean is equal to 95.4 degrees Celsius. Okay, after you get your data log mean, you have to substitute into Q equation. Q dot is equal to HAS delta T log mean. So from here, we have to substitute all the calculated value before. So our H is 92.2 watt per meter square dot Kelvin, and then AS is 2.827 L times with our delta T log mean 95.4 degree Celsius. So here we have L. So bring this L to the left hand side. Okay, your equation becomes Q dot over L, because this is what they want in the equation. The objective of the equation, rate of heat transfer per unit length. So you will get, multiply all the values, and you will get that your Q dot per L is equivalent to 2.49 times 10 to the power of 4 watt per unit length. Okay, if you assume your values of length is equivalent to 1 meter, therefore at the end of this, if you find that rate of heat transfer, you have to state that rate of heat transfer that you get is for 1 meter length. Okay, so from here we can check whether our assumption is true or not. At the beginning of our solution, we have assumed that arithmetic mean is equivalent to 60 degree. Therefore, we can check whether our assumption is correct or not. This is for degree level. For diploma level, your T exit will be given. So Ti plus T exit divided by 2. So this T exit is from your calculation. So you already calculate that T exit is equivalent to 29.11. So you have to add both values. So 20 plus 29.11 divided by 2. So you will get this value around 24.6 degrees Celsius. So it is far from your arithmetic assumption for arithmetic means. Therefore, you have to iterate and assume again until you get this value equal to your assumption value. Okay, this is normally for degree level and above. At diploma level, you will be given the values and the properties. Okay, so here we have Q dot over L. This is as you can see, that is long way on how to on calculation of Q dot per L. There is a simpler method on calculating Q dot over L. After you get the T exit, okay, after you get the T exit, you may substitute into the equation of Q dot equal to M dot Cp Te minus Ti. So from here you can substitute all the values. So your value for M dot Cp is M dot is 2.709 L times with your Cp is 1007 kilogram joule per kilogram dot Kelvin, and then times with 29.11 for your the exit minus with 20. Okay, so here L, bring it into left hand side, so your equation becomes Q over L, and then you calculate this, you will get the value is 2.49 times 10 to the power of 4 watt per meter. It is the same as when you are using the 30 log mean. Okay, that is how you calculate rate of heat transfer per unit length for a tube bank. Okay, thank you.